Good morning, developers. If you are new to the channel, my name is Rob, and it is Computer Science Thursday, CS Day, where we look at some topic that has to do with concept, with computer architecture, how programming languages work. All the other days, we look at implementation details. How do we use this library or this language? Today, it's all concept. And the question that we want to answer is, it's painful to even look at, but why on earth, in JavaScript, Python, and really every programming language, does 0.1 plus 0.2 not equal 0.3? That's nonsense, right? I've got a bunch of question marks there. It's painful to even look at because any child who's had elementary math with decimals knows that this is true. 0.1 plus 0.2 does equal 0.3. And computers are supposed to be good at math, right? So why does it consistently get this wrong? Okay, the reason that this came up is because I was working on a video that talked through why does JavaScript have a big int now. It was implemented a couple years ago. Up until that point, the largest possible integer that JavaScript could accurately represent was just over 9 quadrillion. Okay, that's a ridiculously large number to humans, but it doesn't seem that big for a computer. So it seemed kind of strange. They implemented big int, and that solves, it's a new data type, and it solves the problem. But to talk about why this is necessary, we have to talk about how JavaScript stores numbers. It stores numbers the same way that Python does, and as I was thinking about it, I thought, oh, this is a perfect example to talk through that rather than to put it in that video. It leads to the question, though, that if they store data the same way, why does Python not have to have a big int data type? Why does its integer go to as much memory as you've got? And we will get there. But first, to our question here. How does JavaScript, how does Python store numbers internally? Okay? Memory, right? Memory is the short answer. Let's start here. What is that? What would you say that is? It's not a trick question. That is the number 9, right? Except how do we tell a computer that that's the number 9? Because it isn't the number 9, it's just it's a symbol. It's a bunch of squiggle lines. If you were, had an illiterate person, someone who didn't know math or never seen numbers before, that does not communicate the idea that is the number 9. It is just a symbol that represents an idea. If you open up a computer, okay, now this is going to be really obnoxious. I'd like to start somewhere else, but I don't know how to. If you open up a computer, how do you store data in there? There is no data in there. There's no information. There's nothing in there but a bunch of hardware components, a bunch of circuit boards. So a computer not only doesn't know what 9 is, but it can't store the number 9. What we need to figure out is how can we store something that represents the number 9 for us so that when we pull it out. As we could store a picture or something like that, but then what if you wanted to add the number 1? Well, you can't add the number 1 to a picture, so we've got a problem there, okay? Let's take another step back, okay, and kind of reset everything. One more obnoxious comment. What is a computer? Okay, what's the simplest way, from as high up as possible, how do we describe a computer? I'm going to say that a computer is nothing more than a giant state machine, okay? In spite of all the crazy, awesome things that are going on with AI and all the amazing things that we think computers can do, the truth is, at least until quantum computing becomes a thing, all a computer is that, okay? Not even ones and zeros. I know it looks like a 0 and a 1, but a computer has a state machine. What's a state machine? A state machine is like a light switch. It just manages whether something is off or on, 0 or 1, off or on, electricity going one way or the other. That's what a state machine is. It just so happens that a computer has trillions or quadrillions or billions, whatever it is, of these little pieces of state, these light switches, so to speak, right? Transistors or whatever you want to call them. And the reason for this is, this goes back to how computers were designed back in the 50s and 60s. This is not what a transistor looks like, but for illustration purposes, current comes down and then either it's open and it's able to pass through, or it's closed and it doesn't go through. This is the basic architecture that we still use today. Even modern AMD and Intel chips can still run machine code that was written back in the 70s and 80s because things haven't really changed that much. The processors, instead of having 10,000 transistors, have billions, or we're probably getting close to trillions now. We can do the same repetitive task just way faster and way broader because we have more but we have more state, more little light switches, so to speak. Okay? So again, a computer in the most simple term is a huge state machine, meaning it has a zillion light switches. How do we take the number 9 and give it to something that only has a concept of whether a bunch of light switches are on or off? Okay? That seems very strange, but that's where we're starting from here. So the number 9. Let's think about our own system. Okay, and I'll go ahead and put it down here since maybe you're dying to know. We're going to come back to this in a second, but computers are binary. That's what this is right here, the transistor, the 0 and the 1. That is essentially a binary system where you have either off or you have on. You don't have 0 and 1. Now that's how they're communicated, but really what you have is off and on, and that is it. How do we do our numbers? And it's really helpful to think about our numbers before we talk about the binary system, because if I was going to teach you Java and you knew JavaScript, I would use JavaScript to help you understand Java. Same thing like if you knew English and I was trying to teach you German, I would use your English that you already know, that you just maybe don't realize you know, to help you understand German. If we want to write, let's make a bigger number here, the number 127. Okay? We have a 10 base system or a decimal system, meaning there are 10 digits for every slot that we have. In this first slot is known as the ones. Everything in there is a single digit from 0 to 9. So those are our 10 digits in the ones place. This next one, the 2, this is known as the tens place. Even though we have the same digits in there, 0 through 9, these are a factor of 10 bigger. So a 2 here isn't the same as a 2 here. It's a 2 here times 10, which is actually 20, right? I know this is oversimple, and it's only because it's so second nature to you that you've seen numbers all your life that you're so used to this. What is this one? Well, this is the hundreds place. Why? Well, there's the number 1 there. How is that 100? Because we take the number 1 and we multiply it times 10, which is 100. That's how we get the number 100 there, okay? It continues on. You keep multiplying times 10 because we have 10 digits. The 1,000th place, 10,000th, 100,000th, millionth, it's so on and so on, okay? So that's our system. Binary works exactly the same way. And I know it doesn't feel like it because it hurts my head sometimes to do binary, but it is exactly the same thing. Instead of having 10 digits, it only has 2 digits. Why is this useful? Because with computers, we only have an off and an on. Off is going to represent 0 and 1 is going to represent, on is going to represent 1. It works the same way starting from the right, meaning the smallest number is on the right. So 127 here, the number 7 is the smallest one, it's on the right. We start from the right here. This spot in a binary number is also the ones. What are our options here? Well, it's only off or on, 1 or 0. Over here, it could be 0 through 9. So we had 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So there's a lot more options here, but it's the same concept. We just have 2 digits to work with. Just like over here, okay? If you were to add 1 to this number, what happens? Well, you start as far right as possible, and you bump that up to the next digit. We go to 8. You add 1 again, you bump up to 9. You add 1 again, well, you can't go above 9. 9 is the biggest digit for that place. So this resets to its smallest number, and you increment the next place up. Why? Because there are 10 digits here, and this one is 10 times bigger than that one. It's the same with binary. If we use up our 1 here, so binary, in binary 1 is the same as it is in decimal, but if we wanted to add 1 to this, we can't hold 2 here because this only has option of 0 and 1. So we fall over to the next one, and this becomes 1. Again, that's our only choice. This is the 2's spot, okay? If we fill up both of these, so just like over here, if we had the number 9, we've filled up one spot, we have to go to the next. We get to the number 99, we have maxed out both of those, we have to fall over to the number 100. Well, maxing this out would be a 1 here and a 1 here. If we add 1 to that, we have to fall over to this. 1 here is a 1. 1 here is a 2. 2 plus 1 is 3. 3 plus 1 falls us over into the 4s. Okay? We keep going down the list. We have 8, 16, 32, 64, 128, 256, 5, 12, 10, 24, and so on. The binary system is base 2, or it is powers of 2 in every single slot here. Why? Because there are 2 digits, and just like in our system, this number here is 10 times whatever that digit is. The same thing's happening here. We have to fall over, which means every time we have maxed out, we double to the next number. So if we have a 1 here, that's just 1. Let me switch colors here. If we have a 1 here, then we have a 2. We don't ever have to think about 20 or 30 or 40 because there's only 2 options, 0 and 1. If we have a 1 here, we have 4. So it would be 4 plus 2 plus 1 makes 7. That's always going to be 1 less than the next big number up, just like 100 is 1 more than the number 99. If we have a 1 here, that means we are using 8, that this is 1 as a factor of 2. How so? Well, let me show you. The 1's place is really 2 to the 0th power. We're in the 0 slot. This one is really 2 to the 1st power. This one is 2 to the 2nd power. This is 2 to the 3rd. This is 2 to the 4th, 2 to the 5th, and so on. It's the same over here. This is 10 to the 0. This one is 10 to the 1. This is 10 to the 2. The next spot would be 10 to the 3. 10 to the 3rd power is 1,000. That would be the 1,000th spot. Okay? I hope you're seeing the synergy here because they are exactly the same. Math is perfect. The numbers are perfect. We just happen to use different. When you switch bases, when you switch the numbers that you're multiplying, it gets confusing. Tens are very, very wonderful, partly because you have 10 of these and for other reasons. But let me clear this up real quick. We're going to move on to the really confusing part, which is fractional numbers. Okay, I'll be right back. Okay, so we got a clean board. Before we move on to fractions, which is really going to boil your brain, let's do a couple of regular binary numbers. Let's do the conversions because this will help a lot. Let's take the number 13. Okay, we'll do this in binary, but first let's actually go ahead and do another decimal one. We'll take the number 127 again. If I said write the number 127, now you would do it instantly because you already know what it looks like. But if you were a computer and you had to think about it, okay, what you do is you would think, okay, what's the largest digit that I'm going to need here? Because that's what I'm going to write first. And in order to find that, you go left, starting from the smallest number, and you go left until you hit a digit that is too big, that is bigger than our number. So this is the ones. This is the tens, this is the hundreds, this is the thousands. So the smallest number we can possibly represent in that 4th digit would be 1,000, 1 with all zeros. That's too big for 127. So that means we have found our biggest digit. It will be that 3rd digit, okay? This is like absolute elementary math here, but it's going to help with binary. So we know that we have 3 digits in here. We just don't know what they are yet. We start off at 9. 9 is too big. 900, 800, 700, 600, 500, all the way down. And then we realize, okay, 100. That is the first number that's not bigger than our number. So we've got 1 in the first slot. We don't know what's in the other 2. How do we go on from there? Well, we take 127 and we subtract 100 from it because we just used 100. We're left over with 27. It's not fair because we're doing this in decimal. That's obviously the answer. But 27, as we start going from right to left, what's the first number that's not too big? Well, if we get to the 3rd, we've already used our 3rd decimal, but obviously 100 is too big for that. So the 2nd decimal, we start off at 90. We keep working our way down until we hit 2, which is 20. 20 is not too big, so that's what we put in here. We subtract 20 here. We're left over with 7. 7 goes in the last slot. Okay, that's how we write the number 127 in binary, in decimal, I mean. If we are going to do number 13 in binary, we're going to do the same thing. Starting from the right, and I'll jot them down here again. We've got a 0, a 0, a 0, and so on, okay? This is the 1s, this is the 2, this is 4, this is 8, this is 16, and this is 32. 13, if we start from here, we go until we get to a number that's too big. 16 is too big. Okay, we can't represent 16 to 13 because it's too big. So it's going to be the number 8 here. So that'll be our first one. A 1 right there. All right, so we take 13 and we subtract 8 from it. What does that give us? That gives us the number 5. So now we have to represent the number 5. We start going that way until we get to a number that's not too big. Well, 4 is the last number that we could possibly use. Okay, so we subtract 4 now from 5. We're left over with 1. What is the first number that we come to here? It's the very first one, which means this last one has to be 0. That is a representation of 13 in binary. 1, 1, 0, 2s, 1, 4, and 1, 8. So 8 plus 4 is 12, plus 1 is 13. That's how we do binary, the same way that we do our base 10. It just hurts our head. Okay, and here's our pivot. How do we do fractions? Fractions are going to work exactly the same way as they do in our system. I know you're probably getting tired of hearing that, but let's say we had the number 127.436. Okay? What is this place, the 0.4? What do we call that? That is the 10th. What do we call this one? The third, or the number 3 there. That is the 100th. What do we call this one? That is the 1000th, and so on, right? What are we really doing here? Remember, there's 10 digits that we have to work with. What we really have here is 1 divided by 10. What we have here is 1 divided by 100, which is really just this divided by another 10. What do we have here? Well, it's 1 divided by 1,000, which is really just this divided by another 10. As you move this way, just like going that way, we multiply times 10 for every new digit. Going that way, we divide by 10 for every new digit. We're going to do the same thing with binary. If we want to represent a number in a fractional number in binary, going that way, instead of dividing by 10, we're going to divide by 2. So we've got, let's say, so we'll take this. So we've got 1101. That's the number 13 in binary. We have a decimal place in binary, just like we do in decimal. The first spot here, I'm going to put a 1, and I'll just put some random stuff here. Okay? What is this number that I just drew? Well, this spot here is the 1/2 place. This spot here is 1/2 divided by 2, which is the 1/4 place. This spot here is the 1/8 place. This spot here is the 1/16th, 1/32nd, 1/64th, 1/128th, and so on. Okay? The reason this hurts my head so bad is because it's hard for me to remember what 1/32nd is in our base 10 system. Okay? So here's what we're working with. The number that we've got here is 1/2 plus 1/8, and I don't know why I skipped over, that's very strange. This is the 1/32nd spot, and this is actually the 1/64th spot. I don't know, I just had a little visual fail there for a second. We've got 1/2 plus an 1/8 plus a 32nd. So what we actually have here is a binary representation of the number 13.65625. Why? Well, 1/2 is the same thing as 0.5. 1/8 is the same thing as 0.125. And 1/32nd is the same thing as 0.03125. You add those together, you end up with this number, which is actually in our number system this. Okay? So we finally have hit the moment of truth here. How do we represent the number 0.1? Okay, I'm going to clear this off quick. So I have us a new chart up here. Okay, we've got along the left-hand side, or the first thing in each one, is 2 to the negative power. And if you don't remember how negative powers works, all it means is you take 1 divided by this number. So in this case, we've got 1/2, which gives us 0.5. In this case, 2 to the negative 2 power is the second digit to the right of the decimal. You divide 1 divided by 2 and then divide it by 2 again, which is 1/4 or 0.25. 2 to the negative third, you can see on down. I've got the first 7 places that we can work with. Let's actually do one more before we do the hard one here. If we wanted to represent the number 0.625, how do we go about it? Well, we look for the first, we go from the top down here and look for the first number that's not too big for 0.625. This isn't too big. We can use this first number. So we'll have 0.1. Okay, we just pulled 0.5 out of our number, so we do 0.625 minus 0.5 gives us 0.125. Okay? We start again from the top, looking down until we get to one that's not too big. Well, this one's too big. That's bigger than 0.125. Oh, there's 0.125. We got 0.101 is 0.625. Okay? I picked easy ones for a reason. If we want to do the number 0.1, okay? We do the same thing. Start up at the top. When do we get to one that's not too big? Well, that's too big, that's too big, that's too big. Okay, we found one. So we've got 0.000, too big, too big, too big. This one's not, so we've got a 1. So we do 0.1 minus 0.0625. So we'll put zeros in there, and the answer that we are left over with is going to be 0.0375. Okay, so we start at the top, and we're looking for something that's not too big for 0.0375. Okay, we found one. It's this one. So it's the 5th spot. So we have another 1. We take this, 0.03125. Now, I don't know if you can see what's coming here, but this goes down to 4. That's 2, 7, 6. So we end up with 0.00625. Now, I wish we could use this one, but there's a 0 missing at the beginning. This is 00625, and that's 0625. We're going to have to keep going down, 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 down. These are all too small, or rather too big. So the last one we used was this one. We've got 2 more zeros, and then I'll just tell you, we have another 1, and another 1, and then a 0, and a 0, and another 1, and another 1, and a 0, and a 0, and I'm just going to do dot, dot, dot. Okay? This is why this is a problem. Now, we'll still get to how JavaScript and Python store data. 0.1 in decimal is almost the easiest number to write. It's the number 1 with a dot in front of it. You have represented it with perfect precision. In binary, when we only have 2 digits to work with, 0 and 1, it is essentially an unrepresentable number, like the number 1/3. Number 1/3 in our system, and in 10-base system, is this, right? Just keep writing 3, and you'll never get to the end. 0.1 we can't represent in binary without an infinite number of digits, okay? So how do JavaScript and Python and other languages, how do they represent this number? Again, let me clean up quick. So we're back to a clean board. I left our friend up here, 0.1, going out a ways. The question now is, how does JavaScript and Python, how do they store a number like this with just zeros and ones, or offs and ons if you prefer? All right, we use memory, of course, right? That's where data is stored. That's where state is stored, if you prefer as well. We use 64 bits, which is a way of saying that we take a piece of memory and we divide it up into 64 different little parts. Okay, I'm not going to be able to draw 64 lines here, but you get the idea. Okay, so we've got 64 different parts. And why 64? Because of something called IEEE 754. And I could potentially do another video on this. It's kind of actually what we're going to talk about, the basics here right now. What is IEEE? It stands for the Institute of Electrical and Electronic Engineers. And it was founded back in 1963. It is sort of the big shot group of international people who establish standards for how electronic and electrical things are supposed to work. This was really important in the early 60s because people were building computers and they were not following any standards. So there was no way for one computer to talk to another, or if you wrote a program on one computer, it almost certainly wouldn't run on another. We are so spoiled or so lucky or so whatever. HTTP as for instance, the internet protocol, we can pass data between a coffee machine, a PlayStation, an iPhone, a browser on a desktop. As long as they have browsers, we have a standard, and it's because of organizations like IEEE. They came up with, and IEEE actually comes from the American Institute of Electrical Engineers, which is like late 1800s. So it's sort of a little progression. It's kind of fun if you want to go do some research. IEEE 754 is the standard for, you probably heard this before, double precision floating point. Okay? This standard decided or defined how computers who want to use this standard at least are going to work with double precision floating point numbers. What we have here is a number with a decimal point in it. okay? And that decimal point is going to float. It's going to move depending on a couple different factors, which we'll talk about here in a minute. Double precision, there are two different versions of this. The single precision, or the original one, was 32 bits. Double precision means we have 64 bits to work with. Okay, so what goes inside of these different bits based on this IEEE 754 thing, this double precision floating point? We've got 64 slots to work with in our memory. Well, in the first slot goes the sign, negative or positive. If the number is negative, then we put a 1 here. If the number is positive, we put a 0, or we leave it off, if you prefer. From slots 2 through 12, so we have 11 memory registers to work with here, we put in there what is known as the exponent. And the exponent is, we're going to rewrite our number in a minute in scientific notation. This is going to tell the machine how many powers of 2 to raise this to get the decimal in the right place. Remember, it's of floating point. We're going to move that decimal. This is going to decide how far we move it, right? The rest of it, so it's going to be 13 out to 64, is called the mantissa. And I know that's a scary sounding term. It's really not a big deal. The mantissa is the actual number that we have. It is as far out as we can go. And this has a size of, I'll put in parentheses here, 52. Which means the biggest number that we can put in here, or the most accurate or the most precise we can be, is as big as the mantissa is. We cannot get bigger than 52. So this number here, the most we can put in the mantissa here is going to be 52 digits, and we need millions for that to make sense. Okay, I know 52 seems like a lot, but it's not going to do the trick. Okay, we'll come back to that in just a second. Let's represent a number here in IEEE form. We'll do the number 9.375. Okay, so the first task is to write this in binary. Okay, and we do both sides separately. So let's do the integer part first. How do we represent 9 in binary? Well, we kind of already did this. We need an 8. We don't need any 4s. We don't need any 2s. And we need a 1. So that's the number 9 in binary. How do we represent the number 0.375? Well, we skip over. So we got to have our point there. We skip over the first one because 0.5 is too big. We use a quarter. And then we use our 1/8. Okay? So that is a perfect representation of the number 9.375. in binary. We've got the integer on the left and we've got the decimal on the right. Okay? Now to actually put it inside of memory following this standard, which is what JavaScript and Python use, we have to do scientific notation, but we still are in binary, which means we have the number now 1.001011. It's exactly the same number, but we moved the decimal place over. We have to put at the end now times 2 to the what? Well, how many places did we move it over? 1, 2, 3. So that is the scientific notation of the binary version of that number. Okay? Now, we take this thing, and what we put in here, well, it's not negative, so we have a 0 in the first one. For the exponent, well, we have 3, but we have to add a bias to it, okay? And we're not going to talk about that now. You can go do a little bit of research if you want to, but the bias for double precision is always 1023. So what we put in these 2 to 12 slots is the number 3 plus 1023, which is 1026, which in binary is 1. We have 8 zeros, 2, 3, 4, 5, 6, 7, 8, and then we have a 1. And then we have another 0, okay? I overrode on top of the lines because we don't actually have 64. So we've got 0 for the sign. We've got from 2 through 12, the number, the exponent, which has a bias plus our exponent. Again, if you want to do a little bit of research, it allows us to do negative and positive numbers without having to fiddle around with that. Don't worry about that. The next thing that we put in there is the number itself, which in our case, the mantissa, is the rest here, which is 0, 0, 1, 0, 1, 1, and then we round it off with zeros. Okay? If you want to write the number 9.375 in JavaScript in memory or in Python in memory, this is how you do it. With these 3 pieces, the sign, the exponent, the mantissa, the sign is negative or positive. The exponent is, once we convert from the binary version into scientific notation binary, how far we move the floating point. That's the number there. The mantissa is all of the actual numbers in binary, okay? And it's going to be both, right? Inside of this number contains both the integer and the fraction. The exponent figures out how far do we move to get the decimal back in the right place, okay? That is why these numbers are not equal, because we only have 52 digits to find precision on 0.2 and 0.1. And when we add them together, the computer's going to have to round stuff off, because it's sort of like we did 0.3333333, and we ended up like a 4 at the end or something like that, or it rounded it up or down for whatever reason. We end up with imprecise numbers is essentially what happens. Okay? Now back to the last question that we need to answer here. Why, if both Python and JavaScript use IEEE 754 to store numbers, why does Python not have an issue when it comes to any size integer? In fact, if you want to start a loop and just multiply times 10 and store that, it will run until your computer runs out of memory, because it doesn't have a max integer. JavaScript will not do that. Well, tell me this. How many number types are there in Python? We have an int, and we have a float. Okay? The float is what implements this. Integer doesn't implement things this way. How many different data types are there in JavaScript? There is this thing. And that's it. It only has number, which means it has to implement this for its all decimals. It also has to use the same thing for integers, and Python doesn't struggle with that. So Python has a mantissa for its integers, but as the numbers get bigger, it just keeps adding or using more bits, so it's not stuck on 64. It can go out to 1,000,000 if you've got 1,000,000 to work with. JavaScript can't do that because it's got the same data type. That's why big int was necessary, because we couldn't store everything in here. And we can illustrate this over in the console. I've got the browser console pulled up. If I drop in here number.maxSafeInteger, it's that number I mentioned, 9 quadrillion and change. Why is it that? Well, how big is our mantissa? It's 52 digits. With the scientific notation, we've got that 1 at the very beginning, the 1 dot. So if we do 2 to the 53rd power and subtract that 1, that is where that thing comes from, because the mantissa will not allow it to get any bigger. If we do 2 to the 53rd and we add 2, that's not right. If we add 3, it just hopped 2 spaces. If we add 4, right, it doesn't change at all. 5, 6, you don't know what's going to happen, because JavaScript cannot be more precise, because it's using that IEEE 754, where we've only got 52 digits to work with. If we come over, I'm on Windows, so I'm on PowerShell. If I open up a Python prompt, if we do pow and we hand it 2, 53 minus 1, that is the exact same number, but Python can add 1 and get the right answer. 2, 3, you get the idea. We can go as big as we want in Python and have no precision issues, because this is an integer which is able to float the mantissa as many bits as it needs to. As just like kind of a final thought, which is kind of fun, if we import sys, there is a concept in computer science, and certainly all programming languages anyway, where if we do sys.floatinfo.epsilon, this will show us the smallest possible value, at least relative, not negative numbers, but this is the number right above 0. If we fill the mantissa up with all zeros, so 51 zeros, and that last spot has a 1 in it, that is what this number is. So this is as precise, or the smallest possible number that we can use, so as precise as we can be in our floating point numbers. If we come back over, JavaScript has the same thing here. If I do number.epsilon, you just saw it there. This is exactly the same numbers as what we saw over in Python. I hope that this has been enjoyable. Lots of different concepts here, binary fractions, IEEE 754, and how to implement floating point and so on. It all really comes down to binary fractions are miserable to represent, because we can be perfectly accurate with any positive integer and really any negative integer, but fractions make it hard. That's why, come back over one more time to the terminal here, and we do 0.1 plus 0.2, we get that goofy looking thing, because fractions are nasty in binary. The computer's doing the best that it can, and This is the type of stuff that will make you a really, really good software engineer, a really good developer, not only knowing how to code, but knowing how your coding language works. I hope I will see you in the next one. I'll drop a few links of some others if you would like to check them out. Thank you so much for watching.